environment could be calculated similar to what I showed about setting up that database where you have make measurements from a test device at various places within the environment, and you know where the device is located. You can measure the distance to the terminal or to different access terminals, and then you will have the situation. You can make a chart of different distances as on that previous slide. Let me go back a few slides. One moment. You can make a lot of measurements like we have here and determine, I won't go into the details of determining this regression curve. This will give you a value of n where the d0 will be 1 meter. We can see that the variances are very relatively large here. The standard deviations we have here are relatively large. Remember that 3 dBs would be a factor of 2 in the path loss. So this is what you can expect if you make these measurements. If you have an environment with many reflections and boundaries, that's about the best you could do. If you use the path loss method. The path loss method is best to use when there are very few reflections or in the free space situation. Okay, let me go to the question and answers. Okay, there was the one question is in, let me go back to, let's see where, slide 7. A one-direction situation, how accurate is the synchronization required between the transmitter and the target? First of all, if there is a drift, as time goes on, the difference between the transmitter clock and the receiver clock will go up. If the difference between the transmitter clock and the receiver clock is, for example, 3 nanoseconds, then the or 3.3 nanoseconds, then the distance can be determined within an accuracy of around 1 meter. So if it were, say, 30 nanoseconds, then it would be an accuracy of around 10 meters. And again, this difference between the transmitter and the receiver would get greater as time goes by because the clocks are not synchronized. There is drift between them. So how accuracy is the synchronization required? Absolute synchronization would be needed, or having atomic clocks, again depending on the accuracy determined, having atomic clocks during the time period where the clocks are free running. It can be determined how different the clock times would be, and taking the difference in clock times, multiplying by the speed of light would give you an estimate of the type of accuracy that can be determined using that method. Okay. Let me go, the next one regarding slide 6, real value. I'm not sure what that refers to here. Okay, let me go on to the next question that I can answer here. I am used to seeing path loss expressed with higher loss in practice. Instead of 20 log, it is often shown as 30 log or more to account for losses in the transmitter and receiver. Again, this, whether it is 20 log or 30 log, depends again on the particular environment. Here, for example, in this curve here, we see n is equal to 3. So here we would have 30 log in this particular case. In a different environment, with many of these measurements, the slope will be different. This number, let me get back to the pointer again. This number would be different. In the case of the free space situation, we would have 20 log here. Okay, so this will be 20 log in free space. So if you see differences, that is because there are differences in the reflections and the effect of the reflections on the relationship between the path loss and the distance between transmitter and receiver. Okay, slide 19, let me go back to slide 19. I mentioned here the far field. The largest dimension of a horn antenna is the diagonal. I would agree with that. Again, when we're talking about a horn antenna, for normal horn antennas with only maybe even only a few centimeters of dimensions, we're talking here about, with wavelengths, which may be gigahertz. We see that the distances between the antenna being in the far field would be only multiple tens of centimeters at the least. And also note that this is a rule of thumb type of a limit, but there is no direct boundary between far field and near field, but this gives you an indication of how you can start using these formulas depending on the distance between the transmitter and receiver. In the case of a small horn antenna, we're talking about tens of centimeters at the tens of centimeters would be the minimum for the far field. Okay. Here is slide 21. What is the question on slide 21? Is regression experiment design technique used to determine the optimal lambda or the frequency? I don't think so. I think the frequency is determined by other means, of course, by using relatively low frequencies. High frequencies, again, you wouldn't get accuracy, but the relationship reflections are very dependent on the frequency. Normally the frequency is known, and regression would have to be determined for a given frequency, and you wouldn't determine the frequency or the wavelength according to the results of these preliminary measurements. Although there may be situations where frequency would be determined, but I don't think so. The different frequencies are given here because these are the frequencies that happen to be used in this particular case, and these are the results that were obtained. Again, very, very general. This gives you a very, very rough. Obviously, all retail stores are not the same. Offices are very different. Factories are very different. This is just giving an example of how this exponent and the standard deviations could change, but this will not necessarily give you a very good indication of what to use in a particular environment. Another question. Just to confirm, in the D2A method, only the fixed nodes need to be in sync. The object doesn't need to sync with any of them. That's exactly correct. Exactly correct. The TDA method, the fixed nodes have to be, the clocks have to be synchronized, and the object clock does not have to be synchronized. That's correct. Slide 23. Let's see, slide 23. Equation for Dn. Dn is a, That's a good question here. Let me see how I can answer it. I think I should have given this here. I thank you for pointing this out for me. This dn actually is it's a distance from the point of view of the a number which is related to the different signal strength. Yes, S is signal strength. S is the signal strength. Here, the signal strength S with a superscript is a signal strength in the database. Here, there are, for each point in the database, there are 3 different signal strengths. Here we see this summarizing symbol here from 1 to 3. So this I would be from 1 to 3. For a given n is constant, and you would get the sum of 3 different values, the square root of the sum of 3 different values, 3 different measurements of signal strength from the 3 different axis points would be plugged into here, and this would give you the so-called distance, not as far as a physical distance. This is not a physical distance. This is simply an indication to determine its absolute value. Doesn't really matter. What matters here is to get a D value for each of the n points in the database. In other words, you can make a chart here, call it D superscript 1. Do these calculations between this online vector S without the superscript. This would be S1, S2, S3. Make a calculation for each of the n values in the database. You will get a particular number. Its actual value does not matter here, but you would make a table with n versus values of D. In other words, let's say for values of D will be different for each n. I would say, let's say, have a chart here. Let me say, I don't know if I can easily do this. Let me see if no, I think I need, I don't know if this is, yeah, okay. Let's say we have a database, and here we have, I don't need 3 lines here. Let me just cancel this out. Okay, let's say we have, here we have a value of n from 1 until the whole number, the number of different values in the database, and that would be, I think I could have left it there, the point. It's very difficult for me to do this here, but in any case, we have 1, 2, 3, so on to the total number of values, and here we will have on this here the D values. For each point in the database, there will be a value of D, and all these are calculated for a particular S. This, we have one measurement of S, where the target is located at a time. This expression is repeated n different times. You will have then a table of n values, n1 and so on. And within here you will have numbers which are called D, and then you would take a look at this table and find out which values of n have the lowest value of D, and then you would use these values here in order to calculate by knowing which n values here have the lowest values, you would be able to determine the x and y values. The x and y values of those closest neighbors. The closest neighbors are those that have the lowest value of D. And then you would use this expression here in order to get the estimation of the target position. I hope this is clear. Difficult to do it on one diagram here, presumably, but to again, this is not necessarily meters. This is only a number which indicates how close these measurements here are to the particular signal strength values in the table itself. Okay, I hope it's clear. I have an answer that Miriam finds that it is clear, so I hope that all of you understand this a little bit better. In any case, each measurement of the online, the test, many comparisons have to be made according to the numbers of database points have been taken in advance. Okay, so let's go on. I think that once you look over these after this explanation, I think you'll start to be able to understand this. Okay, let me move on to where we were before, and we will moment. Let me just see here. Okay, let's move on from here, and I'm going to have to speed up a little bit, I think. Okay, another method we talked about two different methods. We talked about the radio propagation, the signals, electromagnetic radiation, propagation, and how we use timing and phase to determine a distance. We talked about the received signal strength, where we can either determine a distance directly or a location directly. And now we have this other parameter, angle of arrival, where we want to determine the direction from which the signal is coming. Okay, to determine angle of arrival, we need a directive antenna. Directive antenna has here, we have a chart of the pattern of an antenna. The antenna has directivity, gain. It has a particular pattern that we have here. There is a beam width, which is often specified, as we can see here, and there is a polarization, which is the direction of the electric field in the signal itself. Okay? The directivity indicates how sharp this beam is, how small the beam width is, means higher directivity. The gain is the same as directivity, except that it takes into account the losses in the antenna. The directivity is more of a theoretical possibility of a given type of an antenna. The gain will always be less than the directivity, but it's the gain which we normally measure, and that's the term that we normally would be using. And we can see here that we have a particular directive antenna. This is the pattern. We want to determine where a signal is coming from. The signal could be coming from here. We're also going to detect it if the signal is coming from a direction. Not drawing it very well. Maybe I should have a line. If the signal is coming from here, we see that the signal strength is much lower than if the signal is coming from here. What we want to determine is which direction the signal is coming from. Note that if the signal is coming from another direction, it only changes a little bit. How do we determine the direction? We can use it by saying we have a movable antenna, rotating antenna. We rotated it to find the strongest signal. signals which are almost head-on in this particular case will also be, and it will be difficult to determine exactly where the signal is coming from. So this signal depends on the ability to determine the direction that the signal is coming from depends on the noise on the signal, or the signal to noise ratio. So and also by the beam width. Obviously, if the beam were much sharper for a given signal to noise ratio, we would still have a much more accurate determination of the direction that the signal is coming from. For a given pattern, the higher the lower the signal to noise ratio, the more fuzzy the signals, more difficult it will be to determine the position of the antenna, which gives the maximum signal strength and gives the exact direction. So this shows here simply that the error in determining the angle of arrival depends both on the sharpness of the beam and also on the signal to noise ratio of the antenna. We see the importance of this here. The further away the target, you can see easily here this gray area, this uncertainty area, assuming that we can determine, or we think we can determine, an angle at two different base stations, reference stations. We can determine a angle which has, the angle has a particular error on it, according to what I just saw previously, and the actual target location, the coordinates of the target, the estimate of the target with this crown on the top, or the caret on the top of the coordinates. This the further away the target is, the larger this area will be, and the larger the uncertainty of the coordinates of the target. So this shows how the accuracy depends on the distance of the target from the stations, given a particular signal to noise ratio and the beam width of the antennas. Okay, and this is a way of determining the error from the difference between the true position, wherever it happens to be, and the estimated position. This estimated position is estimated according to the angle measurements at the, in this case, two different reference stations. Okay, it's possible to make these measurements, this angle of arrival measurements, by instead of having directional antennas, having omnidirectional antennas, and using a geometrical relationship between the locations of these antennas and the direction of the wavefront of the signal. A wavefront means that the signal is coming from this direction. It will be received at the two different antenna elements, and at the wavefront, the phase of the signal. In other words, we assume that the target is far enough away that the distance to this point on this wavefront, the distance is the same. Obviously, this distance will be the same if the target is very far away. This line, actually, in real life, this would be a semicircle, but this semicircle would be very, very close to a straight line, and the phase would be the same all on this wavefront, but all points on this wavefront. Now, this point on this wavefront arrives at this antenna, antenna B. We will assume that this phase, whatever phase it is, again, phase has to be compared to something. Whatever the phase is, it will be considered the reference phase. the signal, when it receives a little bit later, because it goes a longer distance, the target is here, say, and the signal goes a longer distance to get to the antenna element A, there will be a phase shift according to this length A, and this phase shift is determined by this relationship here, a simple trigonometric expression, which depends on the wavelength of the signal, the wavelength, and the distance apart between the two antenna elements. So this gives us a relationship between the phase detector and the phase detector, the phase difference between the signals from the two different antenna elements, and the direction of the angle of arrival of the signal from the target as compared to the bore sight direction. Okay, so we have now a relationship between the angle that we want to determine, the angle of arrival, and the angle that we can determine in a phase detector. And we can make a plot of this with two elements as we just had here, and we can see that we get a relative straight line over a excuse me, over a relatively wide range of angles. And here we can determine, if we know the output angle, we can determine the angle of arrival within approximately, depending on the accuracy required, between something like plus or minus 100 degrees. Okay, so here is how we can measure angle of arrival without using rotating directional beam antennas, which we're normally used to seeing in radar systems, for example, even though now most of them would be using this electronic method of electronic scanning method to determine the angle of arrival. Okay, this has advantages according to the time of flight methods. It doesn't need cooperation. It's not dependent on the modulation. No synchronization is required. Either mechanical or electronic scanning can be used. And as we saw earlier, the noise or also interference in multipath will limit its accuracy. Okay, so again, now we've already discussed the methods used in that very, very early slide where we saw how to convert angle of arrival and row measurements, distance measurements, to location. Okay, I have some practice questions here. I think we're going to take a short break on these practice questions till 20 minutes after the hour. Take a look at these practice questions. If you do submit any other Q&As in the meantime, I'll take a look at them, and we'll go through these very, very briefly when we come back. So take 5 minutes to look over these and see if you can find the answers. Tara, if you can put up that polling there, that may be fun for the people to put their answers in and give me some indication how they note how they answer these questions.
Okay, yes, I will do. I'm opening the poll now. So hopefully everyone should see that they now have access to the poll. You could submit your questions your answers, for these practice questions, and we'll go over them shortly. And what did you say, 5 minutes? So 20 minutes?
20 minutes after the hour.
Great. Okay, perfect. Thanks, Alan.